How's everyone feeling? I think everybody's tired. So we not only have to worry about AI, I guess, we have to also worry about worms. Looks like it. This was an article a few days ago. I think an editorial on the future of AI and how it's threatening humans. Actually, I think you would have heard that there are quite a few number of AI experts around the world. I think in the hundreds have signed this so-called petition warning humans that AI is coming and may lead to the death of humans and not AI. So I'll just go through a brief timeline of how this all started. Not very long ago, actually, but probably 50, 60, 70 years ago. AI was apparently born in 1955. There was somewhat of a winter during the 60s, 70s, and 80s. And then I think a lot of you, or some of you, may remember that this system called Deep Blue played the chess champion Garry Kasparov. Some of us here are old enough, but a lot of you I know are born after this, 1997. But Deep Blue beat Garry Kasparov 25 years ago. In 2011, we have Siri coming in to play, and then something called Watson, which was apparently a failure by IBM. And then more recently, this system called AlphaGo, which beat the Go champion. So apparently Go is quite complex and much more difficult than playing chess. But the system has managed to crack this as well. So AI in endoscopy have got a few different connotations. You can see there's machine learning, there's sort of speech recognition, text to speech or speech to text. A lot of us and a lot of this where we are involved with endoscopy per se is with image recognition. And there's other things like natural language processing as well as robotics and whatnot. So the number of publications has increased dramatically or drastically. As you can see there, in 2020 it just jumped up many folds, and there's just more and more and more of AI research coming in. It all started from an endoscopy perspective, as I mentioned, with image recognition and mostly with colorectal polyps. So I'll just try to be quick and brief and try to discuss some of the interest. And as I said, this is moving so quickly that almost every day you see a new publication coming up with AI in endoscopy. So in Barrett's esophagus, you would have seen this slide before. It's quite difficult to kind of make out where an area which was biopsied and has come back as a cancer. As you can see, this could be an area which probably showed the cancer, and I showed this slide yesterday as well, but obviously that's just a previous biopsy site. So we went on looking and we found this area which has got abnormal pit pattern and vasculature in keeping with an early Barrett's cancer. But perhaps we don't need to rely on the human eye anymore. And AI can help us with sort of picking these things up. One of our PhD students, Jin Tan, together with my colleague Asif and a few of our other collaborators, have looked at a systematic review and meta-analysis looking at what is the present state of play with AI in Barrett's esophagus. So there are quite a few groups, but generally they tend to publish things time and again. And as you can see here, this group has published 3 papers, and the D group has published another 2. But all in all, it shows that there is pretty high sensitivity and specificity with these AI type models. But all of these generally were retrospective type studies, so studies which looked at images in the past. We're trying to sort of see if we can prospectively look at something not too dissimilar, given that we've got a huge repository of images and videos with more than 500 patients which have been collected over the last 12 years or so. So this is preliminary data which we are trying to publish, and I think Jin and Dilip, who's in the audience here, is trying to write this up, looking at a training and testing set, NBI, white light, multimodal. These are just some of the videos which we have used, and you can see the dysplasia sort of thing changing there, mainly because the AI system has picked up that this to the AI system looks dysplastic, like a dysplastic nodule. All right, so that qualification, if you may, can change from non-dysplasia to dysplasia, but this is a very preliminary model looking at real-time videos, though, of patients who have dysplasia or do not have dysplasia. This is just a similar sort of representation, but looking at an NBI model, and you can see that the AI system is calling this dysplastic. It's called this as non-dysplastic initially, and then slowly as it looks at things with this so-called transformer model, it's basically telling us that this area here is dysplastic. So certainly a lot of interesting work, and it will come a point, I think, from an endoscopy perspective, although we are holding the scopes, we're going to rely more and more on these sort of modalities to tell us what is dysplastic and what is not. As you can see that area is dysplastic in the Barrett segment. This is just the other modules, sort of looking at again, AI models. So we found fairly high sensitivities and specificities. I won't go and bore you with the details of different modules using transformer and what's called as ResNet. And it's certainly an interesting space. With gastric cancer, a lot of work has been done in Japan and also in China. And these systems are quite extraordinary. Look at the accuracy rates here of more than 95% in some instances. And they look at invasion depth as well. I quite like this series of videos because it actually shows a system called EndoAngel ME. And it basically looks at erosions. So it may make the lecture which we heard yesterday moot if this sort of systems can tell us which erosions are non-dysplastic, the top two, versus cancer, which is in the bottom video. So you can see that the system is telling that a carcinoma is detected. So pretty accurate in contrast to what looks like an erosion here, and of course here in the right hand sort of slide, but certainly there was nothing suspicious from an AI perspective. Blind spot monitoring is a quite extraordinary feat. So this is a group from China which looked at a system called YSense and versus controls, and they look at blind spot rates. So you can see a cartoon slowly developing there, basically telling the endoscopists that they have gone, obviously in the esophagus we know that, but it kind of shows as they're progressing which areas were not seen. So reminding the endoscopists that although this is the duodenum, the fundus needs to be looked at, maybe a bit of the cardia. So on the way out, perhaps don't forget that. So as the endoscopist is retroflexing and looking, you can see that the sort of obviously stomach is being created there on the left hand side. Quite a clever technology actually, and just prevents blind spots from being missed, I suppose, in a sense. Still there's a little area not seen there, and as the endoscopist is pulling the scope back, you can see that completes the kind of visual examination at least. So in colonoscopy, there's of course this CADE. So CADE is what's called as detection mode, and characterization mode is called CADX, and the QI mode is called CADQ. So lots of mnemonics and different terminologies. In a nutshell, again, as I said, there are lots of studies coming up. This is a systematic review and meta-analysis of 5 studies, which was published 2 years ago, looking at ADRs. I know in Australia we've got fairly high ADRs, but in this paper they looked at an improvement which is about 12%, 25% to 37% on these 5 studies. Also, they looked at not only diminutive polyps, because we know these systems can probably pick up smaller polyps, but interestingly there was also a change with larger polyps, which is quite interesting. Control 6% CADE, CAD detection sort of module at 11%. it didn't address sessile serrated lesions, and that is one of the issues as well. And there's a time lag delay with the older modules, but increasingly we're seeing that even that is not a problem anymore. 50 millisecond delay is not a problem anymore, because the computers are being produced quick. I mean, the programs are much more quicker, the computers are much more stronger, has higher power of and capability of generating and deciphering these images before sometimes we can even notice things. This is one of the earlier modules, and Mori, Yuichi Mori, who will be visiting Australia soon, has basically spearheaded this endocytoscopy type model. And you can see that the system basically is telling us what's happening. It's got also a funny sound. Adenoma sounds quite pleasant actually, in contrast to probably a cancer. Yeah, so non-neoplastic, these hyperplastic polyps, you saw similar types of images which Professor Sano showed earlier on. So these are obviously non-neoplastic. So what's the beef in this? CADX, these are some of the newer studies looking at more than 1,000 patients. So in essence, they found actually there's no difference between so-called experts, endoscopies alone, and AI-assisted sort of algorithms, 88% versus 88% with the cat eye system. With the endobrain system, again, not too dissimilar, 88 to 90%. But what's interesting is the polyps which were called with high confidence was much higher with the AI system compared to the endoscopies. So maybe that's the plus point. So it's able to basically predict histology in a larger number of polyps compared to the endoscopies, who are experts, by the way. Some issues is that it may not be as impressive in picking up adenomas in high adenoma detectors. For instance, like Cameron may have an ADR of 70%. So will it become 71%? We really don't know. There's this false positive rate as well, and what's called as AI fatigue. So this is quite interesting. These two experts look at 40 videos, and they found that there were 27 false positive AI pickups per colonoscopy. And sometimes it's the bowel wall, sometimes it's the bowel content. When they looked at the videos, they were able to resolve things just by looking. Oh, that looks like a diverticulum, it's not a polyp. But in about 23% of those total videos, they needed quite a bit of time working out, oh, is this really a polyp? Or we can't quite make sense out of it. So that's one of the issues. And when it keeps beeping to you, for instance, like, what's the time now? 3:30, and everyone's tired, you'll just switch it off and finish off the colonoscopy and go home, right? So this is just an example of, obviously we know that's not a polyp. The AI is picking up a villi in the terminal ileum, and then the appendicular orifice. Obviously you don't want to put a snare there and take it off. This actually a scar from a previous EMR resection site. So the AI is trying to say there could be a polyp there, but actually it's not, and we don't want to remove it, of course. We're just evaluating the base and working it out that it's just a benign scar, and that's using NBI with a bit of magnification. So we don't quite need to do anything other than probably taking a couple of biopsies to prove that. But it also picks up the snare, as you can see, right? So that square. So that kind of obviously after a while may irritate people. So we need to differentiate polyps, and we know it's not kind of black and white. We know it's not just remove the polyp or send it for surgery or something, but there are different types of polyps, and we have to try to build an algorithm to look at this. We've tried to sort of do this as well with a few studies, and we found that very quickly accuracy rates were pretty good using a 5-class polyp classification, which was in GI endoscopy, with accuracy of about 94%. So false negative is the other issue. So AI is on here, target mode, and you can see that it's not picking up this lesion. Obviously, you're not going to miss this, right? If you do, then maybe your attention was elsewhere. But these sort of things can happen, and you never know that they could end up being neuroendocrine type lesions as well. So it's quite important to understand that there's false positive and false negative. I mean, we certainly would be able to use AI, I'm sure, with scar evaluations and other sort of visual-like pathologies, but we really need what's called as the ground truth, which I will come to in greater detail. It can now tell us the bowel prep score, Boston bowel prep score, and where cecum is reached. So if, it obviously, it's picking up something. It may be picking up actually this interestingly, maybe it's picking up this sort of question mark sign there, which is there on this device. So who knows, but it can certainly pick not only the cecum, the Boston bowel prep score, obviously large polyps like this is quite possible. It can assess inflammation in IBD, and I won't bore you with the details. Can also sometimes work at natural language processing. And this 12,000 reports, I think, were read within probably 15 to 30 seconds, all right? And it shows that the accuracy rates are similar to a manual report, which would have taken people, I don't know, months maybe to sort of look or sieve through this. So all that may occur soon. AI will probably write our reports, which is not a bad thing, I suppose. You'd be typing away and you realize as soon as your scope is out, AI generates a report for you. So there's issues. Again, this is called the garbage in, garbage out theory. I think some of you may have heard about this. So your data is rubbish, but the model is great. The result is rubbish. The other way around, data is fantastic. Model is rubbish, result is rubbish. So you need everything to sort of work well. So this is quite interesting, the so-called ground truth. So if you take a 15-minute endoscopic procedure with 30 high-definition frames per second, there are 27,000 images, all right, which collectively gets lumped up into, I suppose, a 15-minute video. So what is actually correct and what is not, it's very difficult to say with all of these devices which we have, who determines this? So you need somebody to annotate these polyps, to tell the AI system this is the IC valve and this how a stool looks like, that sort of thing, this how a snare looks like. So somebody needs to do that, and it's gonna be interesting to know who that somebody is and whether there's some sort of inter and intra reliability measures or variations, as well as the patient population, and whether this training data actually match the intended clinical use. So there are lots of databases as well out there, free databases. You can use your own repository. That's what we've been doing for some time, but that's also subject to bias. And then there's trust and medico-legal implications. This is just an algorithm which basically looks at endoscopies and the CAD sort of agreeing that this polyp is TA, and then we sort of putting a confidence strategy into it. But there are times when you think it's an adenoma, CAD says it's hyperplastic. You are highly confident, CAD is lowly confident. So what happens then? We really don't know. Maybe the high confidence prediction prevails. So you are right. But if the other way occurs, would you believe the computer? If the computer says it's an adenoma and you think it's a hyperplastic polyp, it's hard to know these sort of things. This needs to be worked out. So there's so many different platforms. And there's, as I said, user fatigue. Cost is the other issue. And this is really an interesting study by Yuichi Mori's group as well, with Cesare Hassan and Doug Rex. The cost of, it will detect more polyps, right, AI system, So we're going to start taking off more polyps. That's going to increase the cost. But then it may reduce cancer because our ADRs are better, right? So long-term sort of cost effectiveness actually is actually, and this is just a model again, it's not real-time study, shows that there's an incremental reduction of colorectal cancer incidence by 5%, and reduction of cost per patient by $57 US dollars. So savings of $290 million US dollars if everybody in the United States who undergoes screening colonoscopy has AI on top of their routine colonoscopies. So it's quite interesting study, but again, this is a modeling study. It's not in kind of real time. But they also went to this extent to say that somebody needs to then invest, right? AI system. So who's going to pay the upfront cost of $250 million a year to put all these AI systems in each unit? So you have to invest first before reaping the benefits 10, 20, 15, 20 years later. Confidentiality is the other issue. You have all of these systems, and if it goes up to a cloud, who owns that data? I think this guy Tristan Harris said, if you do not pay for the product, you become the product. And then I think he was sacked by Google. So responsibility is the other issue. Still important to understand and master. I think mucosal imaging. That's why most of us are here today, trying to work this out as well. So the future is, it may start checking our performance. We never know. We may have systems which can pick up our ADRs as we go, every colonoscope perhaps. We need to obviously integrate this if it's going to come into play, because right now somebody's just looking at squamous cell cancer, or Barrett's, or gastric lesions, or blind spots. Nobody's kind of collectively looking at it together. So maybe that will come as well. Maybe the AI systems can also look at other things at the tip of the scope, the temperature of the environment within the stomach or the esophagus, or the pH, that sort of thing. We really don't know. Can measure other things perhaps. And maybe assist us with taking off polyps, telling us what to do next. So we may not need Noria telling us how to cut the submucosa. AI may be telling you, okay, this direction, that's how you're going to do it. We don't know. This was just out, and some newer studies saying ChatGPT provides good answers to patients' questions about colonoscopy. So this group, and this published in Gastroenterology a few weeks ago, this group looked at 8 questions, I think, and they found that ChatGPT, if one were to ask ChatGPT about a colonoscopy, they'll get pretty good answers from ChatGPT. And another system, and Andrew's not here, any new AI system can tell normal from abnormal colonic biopsies, and that's published in Gut a few weeks ago as well. So certainly it's coming, but not all systems are the same. So I think there's still some caution advised when we look at these AI systems with regards to training and data sets. We need RCTs, of course. I really don't know whether we need to, or whether we'll wait for them and these sort of AI wave will just take over. I'm not really sure. Maybe it could lead to de-skilling of endoscopies. We won't need to look much anymore. AI is going to tell us where the polyp is. Obviously, if it tells us it's the terminal ileum, we should not put that snare down and try to cut it off, because it's going to be probably a bit of trouble after that. So we really don't know, but this technology is coming, and it's coming quite quickly actually. So with that, thank you, and happy to take questions. If not, I think we're all quite tired, so thank you all for staying back and for coming.